Okay, so here are the values that we have obtained, and I have plotted it in this graph. Okay, so I will enlarge the graph so that you can see how to complete the diagram. Okay, so from 0 to negative 300, how will we complete the diagram? Again, you can look at the equation, but as I have told you in class or taught you in class, you can analyze it through the load diagram. So again, the slope of the shear diagram is equal to the height of the distributed loads at that point. So from point A to point B, our distributed load is downwards here, this trapezoid. Downwards, so negative, but the magnitude is increasing, 100 to 300. So that would be a negative increasing slope for your shear curve. So what I taught you in class, increasing. So you draw a horizontal line because at the start it's flat and then it will increase. So vertical line here. And then you just trace your horizontal line until it becomes a vertical line. There, that's the shape of your diagram. And then we have a 300 Newton concentrated load here downwards. So your diagram would dip down vertically because of the downward concentrated load. And then from point B to point C here, you have a uniformly distributed load upwards. So that would be a constant height, constant slope up to 1000 there. So that's a straight line. And then downwards, again, because of this 250 Newton load, concentrated load, there would be a downward dip here. And then here in this point, take note that we have simplified the diagram here to have a downward 100 Newton per meter distributed, uniformly distributed load. So that should give us a constant slope there. And then here, downward force, constant height. So that will give us a straight line there. And finally, because of our upward force here, EY, that is also 1926.77695, our graph would go up to 0. That would be our curve. Our curve always starts at v is equal to 0 and always should end up at v is equal to 0. So that's how you see if our graph is correct. If you do not get a final value of 0 at the end, then something is wrong with your diagram. So as you can see, we have 2 points of 0 shear at this point and here at this point. And we have to analyze our point of 0 shear because the point of 0 shear could be a location for our maximum moment. So between B and C and between D and E. So how do we determine the point of 0 shear? So for that between B and C, we use the equation. We go back to the equation of between B and C and equate that to 0, the shear. So equating that to 0, we would get a value for x. And to get the moment at that point, we use the equation of moment at that section, MBC, substitute x is equal to 3 to the equation, and we get negative 637.5 Newton meter. Now for the second point of 0 shear, again, it's between D and E, so we use this one. negative 1926.776695 plus 500 times 13 minus x. And equate that to 0, we get this value, 9.1464466 to be x. And then use the equation of MDE here to get the moment at that point. So what we get is 3598.254,872 Newton meter positive. Okay. So now, here is our shear diagram and our moment diagram. The shear diagram has already been completed. Now, the moment diagram, I have plotted the points that we were able to solve for the moment diagram in the table. Now, how do we complete our moment diagram? We need to complete the moment diagram because we have to show that indeed what we will label as our Vmax and Mmax are indeed the maximum values. So how do you complete your moment diagram? Your moment diagram, the slope of the moment diagram is equal to the shear, the value of the shear at that point. So from point A to B, from 0 to 1.5, it's negative 187.5 here. So the shear at that point is negative. Why is it negative? Because it's below the x-axis. Increasing. This is increasing because 0 to 300, the magnitude is increasing. Note that the negative value of 300 just pertains to the direction or the effect of the shear force on your beam. So increasing, so again, you have a flat slope at first and then it increases. So you would have a vertical slope. So you connect that too. And then, the next value that we would have is, well, this is our point of zero shear value, negative 637.5. So from point B here, this is our point B, up to the point of zero shear here, the value is negative. Still, we are still below the diagram, the x-axis, and it's decreasing from negative 600, from 600 to 0. The magnitude is decreasing. So, negative decreasing. Decreasing. So, steep at first and then zero slope here. Diba? Point of inflection. Yan. So, ganyan ang magiging shape ng ating diagram. And then, we would connect that to 612.5. So, look at the shear diagram here. So, for our shear diagram, the value of our shear force is positive increasing. So, from flat slope to steep slope. Here. Kaya, in math, the equation, the shape of your inflection point is always either this way or this way. It would never be like this. It would not be like this. Diba? Lagi namang ganito yung inflection point natin. So, here. And then, we have a downwards movement from 612.5 to 524 because of our counterclockwise movement at the hammer. And then, how to connect 524 to 2,269. Look at this part of the shear diagram. So, again, above the x-axis, your value is positive. And it's decreasing from 800 to 500. So, steep slope first and then decreasing slope here. So, this would be the shape. It's not a straight line. It's a curve that's positive decreasing. And then again, we have the point of zero shear. So look from point D to the point of zero shear. Again, we're still above the x-axis, so positive, but from 500 to 0, that is decreasing. No, first, I'm sorry. We should have a upwards movement first because of our clockwise 1,000 Newton meter load. And then from 3269 to 3598, that would be positive decreasing slope. Again, 3598 is a point of inflection. Now, from the point of zero shear up to the point E here, we have a negative. We are now below the x-axis, increasing from 0 to 1,926. The value is increasing. So we connect that increasing flat slope, steep slope here. So the shape would be like this. Then finally, negative 114.21356, we have a clockwise movement at point E. So our final value would be 0. And that's what will tell you na you have done the right job. If your moment diagram goes to 0. Okay? So now, we note our Vmax and our Mmax. So the largest value, magnitude, in our shear diagram is 1926.77695 newtons. And for our moment diagram, it's 3598.25487.2. Now, for the degree of each curve, I will just erase this. So for our shear diagram, you can look at the equations. Here from A to B, this is a second degree curve. This is a straight line, so that's a first degree curve. There. This is also a straight line, so again, a first degree curve. And then here as well, it's also a first degree curve. And now when we go to our moment diagram, what you have to do is just add 1 to your degrees in your shear diagram. So if you have 2-degree curve for your shear diagram at point A to B, this would now be a third degree curve. And then for point B to C, since this is a first degree curve for your shear, this would now be, for your moment, would be a second degree curve. That goes as well for your C to D. It's a second degree curve as well. And for D to E, it's also a second degree curve. You can check with your equation. That's how to do the method of sections for solving the shear and bending moment diagram of a beam. Thank you.